All right, hello Precalc. Happy Wednesday. Let's get started. So please take out your notes packet and turn to the page of 1.4 for rational expressions. Please pause this recording as students are doing so if they haven't done so already. All right, once you're ready, we're going to be talking about rational expressions, aka expressions that have fractions in them. And in order to do so, we first have to talk about what the domain of a function is. So the domain of a function is what x is allowed to equal. It's basically all the possible x values that you can plug into an equation, and nothing bad's going to happen. Your calculator's not going to go error, error, error. It's going to be all good. So usually we assume that a function has a domain of all real numbers. Typically, with polynomial functions and the stuff that we're used to seeing, our domain is going to be all real numbers, which we represent as an R with that little line through it. Kind of like the paragraph symbol in English, but this time it's an R. That means all real numbers. In interval notation, that is from negative infinity to infinity. Notice in interval notation that we used open parentheses here, open brackets, parentheses, because we cannot actually ever reach infinity. All right, so there are some cases though where our domain is restricted, and we're going to talk about two of those today. I'll put this in red. But there are two cases where domain is restricted. Case one happens when we have a negative number under a root. Specifically a square root in this case. It actually applies to any even-numbered root, but for the purposes of this class, we're just going to talk about square roots. Our second case where our domain is restricted, and it's not just all real numbers, is when we have anything over a denominator of 0. Both of these will produce errors in your calculator, and they are undefined at the x values that either get you a negative number under that square root or get you a denominator equal to 0. All right, so if we do have a square root in our function, or if we do have a fractional function, a rational expression here, how are we going to actually find its domain if it's not just all real numbers? Well, Mr. Smith, let's do that right now. So B, when the function is a fraction, we're just going to set the denominator equal to 0. Basically, you're going to find the x value that makes the denominator equal to 0, and basically the x value that is not going to be in the domain. This actually might be more than one value, as we're going to see later on. So we're going to set denominator equal to 0, solve, then x cannot equal that number or numbers. So once we find the number or numbers that set the denominator equal to 0 or make the denominator equal to 0, then our domain will be all real numbers except x can equal whatever that number is. All right, moving on. When the function is a root, then we're going to set the stuff under the root equal to 0, because we can't have a negative number, which are all the numbers past 0, and solve. Solve for x, find the x values that make all that stuff underneath the root equal to 0. Then our domain x is going to be either greater than or equal to or less than or equal to that number. And under a root, it's typically just going to be one number, not going to get too fancy. All right, so that's when we just have a root. When the function is a fraction with the root in the denominator, oh my god, we just combined both of our two restrictions. Restriction 1 was that, hey, having a negative number in the root. Restriction 2 is having 0 in the denominator. If we have a root inside the denominator, we have something blah, 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 over some stuff in the root. Okay. Same restrictions apply. We're going to set stuff under that root equal to 0. We're going to solve. Then x, our domain, has to be greater than or less than that number. Why is this different than part C? Here's an example. I'm going to use this blank page way up here. Hello, old notes. Here's an example. You don't have to write this down. You can just look if you want. If we have the function 1 over the square root of x, and let's compare that to the function of the square root of x. So let's start with the square root of x. That domain is basically, well, let's follow the steps that we just laid out, which were when the function is a root, set the stuff under the root equal to 0, solve, and then x is going to be greater than or equal to or less than or equal to that number. So here, all we have underneath the root is x. So x equals to 0. When we put 0 in for x, that makes everything under the root equal to 0. Okay, now we have to determine, are we going to be greater than or equal to or less than or equal to? Well, if x is less than or equal to 0, then x is only negative numbers, and we can't have a negative number inside that root. So x must be greater than or equal to 0. The same case would apply here, except if we did plug in 0 for x, if plug in 0, we would get 1 over the square root of 0, which is, well, the square root of 0 is just 0, because 0 times 0 is 0. We would get 1 over 0. Oh no, that's undefined. That is why if we have a square root in the denominator, we're just going to choose between either greater than or less than. We cannot be equal to 0 because we're in the denominator. And if our denominator is equal to 0, we are undefined. Okay, that was a lot of me talking. So let's try some examples. Find the domain of each of these expressions. Okay, first one, we've got 2x squared plus 3x minus 1. Let's look at this. I mean, I don't see any roots. I don't see any fractions where, x could be on the denominator and it could equal 0. So all real numbers. Bam. There is nothing limited. We can plug in any number for x, and we're not going to get an error in our calculators. We're not going to get undefined. B, however, is a little bit different. So B, we have x over x squared minus 5x plus 6. Uh-oh. We've got stuff in the denominator. We've got some x's in the denominator. So let's follow the steps that we laid out before. We know our denominator cannot equal 0. That is a no-no, so we're going to restrict our domain so our denominator does not equal 0. So let's find the values where the denominator is equal to 0. And then those values are what can't be in the domain. So x squared minus 5x plus 6 is equal to 0. We're going to factor this. This should be x. Let's see, so we want to multiply to positive 6, but add to negative 5. So if we're multiplying to a positive, adding to a negative, x minus 3 times x minus 2 is equal to 0. Ultimately, 2 and 3 would make this expression equal to 0. So, for our domain of this entire expression, it's going to be all real numbers except x cannot equal 2 and 3. You can write the word except out if you want to write it out. A comma would also do just fine. All right, let's do part C. Okay, the square root of x plus 6. Oh my god, we have a square root. Can't have a negative number inside our square root. So let's follow our steps from before. Set this stuff equal to 0. Find that borderline breaking point, you know, when we're right in between the negative numbers and the positive numbers. So this expression, x plus 6 is equal to 0. Let's see. When x is equal to negative 6, everything inside the root is equal to 0. So now we have to determine, does x have to be strictly greater than or equal to negative 6 or less than or equal to negative 6? Questions, questions, questions. If at this point you just want to plug in some numbers and see what works, that's fine. Let's start with this top one. If we plug in 0 for x, we would get the square root of 0 plus 6. So we'd get the square root of 6. That works. That checks out. Okay, looks like this is going to be the inequality that we want. Because 0 is greater than or equal to negative 6. It satisfies this inequality. We're set to go. Just to be super sure, let's choose a number that's less than negative 6, like negative 10, and make sure that this doesn't work. If we do plug in negative 10 into this expression, we do get the square root of negative 4, which is a negative under our root, so it can't be that one. Our domain is going to be x is greater than or equal to negative 6. All right. Last two problems of this section. We have the square root of x over x minus 5. All right, so now I see we have both a root and a fraction. So we've got stuff under the denominator and stuff inside the root. So we have to look individually at both of these items and see what makes sense. So underneath the root, we can't have a negative number underneath the root, so x must be greater than or equal to 0. Okay. In the denominator, however, if our denominator can't equal 0, that's only going to happen when x minus 5 is equal to 0. So when x is equal to 5, our denominator is going to be 0. That means x cannot equal 5. Let's look at both parts of these restrictions together. X must be greater than or equal to 0, and x cannot equal 5. So that's going to be our domain. X is greater than or equal to 0, but x cannot equal 5. If you're feeling confident from last night's homework and want to write that in interval notation, that's going to be from 0 to 5, excluding 5, union. Okay, this is a lot. Oops. Don't focus on this. If this should be at your edge of learning. This isn't the goal of today. This is just a little extra bonus if you want it. It's almost like we did from 0 to infinity itself, but since we have open brackets at 5, we are excluding that 5, and the union is joining these two together. That was a lot. Don't focus on that if that's confusing. That's just a little stretch. All right, last one, E. I encourage you to do this one by yourself, so please pause this video and then return once people have tried it. All right, welcome back. You should have noticed that this is a special case where we have a fraction with a root in the denominator. So when we solve for when that stuff under the root in the denominator is equal to 0, we get 4. In this case though, unlike the other typical roots, we cannot include 4 because we've got this stuff in the denominator and our denominator cannot equal 0. So in this case, x just has to be greater than 4. All right, let's move on. All right, I just took a little break because I'm tired. And that was a lot of talking. So if you guys need to take a short little 1-minute break or something, please feel free to stretch, get up, do what you need to do. Just come back in 1 minute so we make sure that we have time to finish these notes. All right. Please pause and come back in 1 minute. All right, so welcome back. Quick review of what we just did. We just looked at the domains of functions, and we found out, hey, we don't want negative numbers inside square roots, and we don't want zeros in our denominators. As a result, we're not always just going to have all real numbers as our domains. Sometimes we're going to have some restrictions, as we pointed out in these 5 problems. Why is this important? Well, because we're going to be working a lot with rational expressions in this class. What is a rational expression? Basically, something just popped up and I don't know how that came up. Well, okay. A rational expression is just a fractional expression. So basically, we've just got some stuff with x's, on the numerator maybe, and then on the denominator as well. We got variables in our numerator and our denominator. All right, so quick review of actual fractions. Let's see. When we encounter rational expressions, they're going to be messy, kind of like this. What we're going to want to factor and cancel as much as possible. It's going to make the expressions look a lot simpler, and it's going to make our lives a lot easier in the end as we move on to more complex math. All right, so fractions, when we add and subtract fractions, we need a common denominator. And we can multiply an expression by 1 in order to get that. All right, and when we multiply and divide fractions, so to multiply, I'm going to put this little star, to multiply, just multiply across the numerator and the denominator. You don't need a common denominator. Multiplication is a bit easier than addition and subtraction. And that's a semicolon. To divide, just multiply by the reciprocal. To divide, just multiply by the reciprocal. You might have learned keep, change, flip. Keep that first fraction, change that multiplication or the division sign into multiplication, and flip that final fraction, aka multiply by the reciprocal. Complex fraction, we're going to come back to that. That'll come up a little bit later. Under E, it says always factor first. Putting this in red because it is important. The more that you can factor and cancel out towards the beginning, the easier your life is going to be. Lastly, let's see, cancel only when we've got parentheses and stuff inside the parentheses on the numerator and denominator that are identical. cancel only when the stuff inside parentheses on the numerator and the denominator are identical. There is one exception to this. If the order is switched, multiply by 1 or by -1 and cancel. What does that mean? On the side here, if we have something like x minus 1 over 1 minus x, basically we can factor out a -1 from that denominator. So -1, and then we are left with -1 plus x, or when we rewrite this again, x minus 1 over negative x minus 1. So if the order between these variables is switched, if there's subtraction, just multiply by -1 or factor out a -1, same thing, and then cancel. So if the order is switched, I'm going to say in subtraction, during subtraction. Multiply by -1 and cancel. We'll see a case of this come up later. Alrighty. Let's do an example. So example A is x squared minus 1 over x squared plus x minus 2. To make our lives easier, let's factor this and cancel out as much as possible. X squared minus 1, that is a difference of squares where our b term is 0. So this will factor to x plus 1 times x minus 1. And if we FOIL this out, we'll see that we will get x squared minus 1. And that denominator should factor to x plus 2 times x minus 1. Awesome. Now, we have an x minus 1 on the numerator and the denominator, so we can cancel these out. Basically, these divide into 1, and we are left with an answer of whatever's left. In this case, x plus 1 over x plus 2. And that is our final simplified answer. Gorgeous. All right, part B. I see division happening in part B's operation. So you might factor first. Honestly, I would prefer to get rid of that division and change it into multiplication as my first step. So we have x minus 4. We're going to keep that first fraction over x squared minus 4 and multiply by its reciprocal. Ooh, I've made so many of these videos now, my voice is going. So bear with me. All right, now we want to factor and cancel out as much as possible. So let's do that right now. X minus 4, that is irreducible, as factored as it can be. X squared minus 4 is another difference of squares. And when we factor that, we'll get x plus 2 times x minus 2. Because that b term goes to 0, and we are all set. X squared plus 5x plus 6. It's going to be x plus 3 times x plus 2. And x squared minus 3x minus 4 is x minus 4 times x plus 1. Okay, so we factored all of these expressions. Now we just want to cancel out as much as we can to simplify it. So let's see, what do we see happening on both the numerator and the denominator? One thing are these x minus 4s. Bam, we can cancel those out. When we divide x minus 4 by x minus 4, it goes to 1. Also see these x plus 2s. And now Yep, that is all that we are left with. X plus 3 over the quantity of x plus 2 times x plus 1. Awesome. Great. Note that x minus 4 doesn't technically have parentheses here. You know, it was just standing by itself. We could have drawn parentheses. Doesn't matter that it didn't have parentheses because we're multiplying these entire fractions together. I got a little lazy, but that is fine. Okay. I wonder if you can see this box that I'm moving around, and I'm scared to delete it if it's gonna end this entire video. So, goodbye box. One more example, number C, letter C. 3 over x minus 1 plus x over x plus 2. All right, we are adding two fractions here with different denominators. Take a second, please pause this video and get these common denominators and try factoring and canceling out as much as possible. So take a few minutes and then join me after. All right, please take a look at what I've written on the screen. Okay. So once I multiplied both of these terms by what I needed to in order to get a common denominator, I distributed the numerators to get 3x plus 6 plus x squared minus x. The reason why I distributed the numerator and not the denominator is because ultimately we still have to add everything in that numerator to get a new trinomial expression here, which turns out to be x squared plus 2x plus 6 when you combine those like terms. I kept the denominator not distributed out in factored form because if I was able to factor this numerator here, then it would be easy for me to just cancel out those factors because I already had the denominator still in factored form. It actually looks like this here is not factorable. So the numerator isn't factorable, so this is our final answer. Yeah. All right. Last but not least, we are going to be working with complex fractions. These are fractions that are happening within fractions, fraction inception. Let's go back up to our notes where it said in part D, complex fraction. What we're going to do when we see complex fractions is add and subtract first. Add and subtract within the numerator, within the denominator, and then do the rest of the stuff from there. How does this look in practice? Let's look at part D, example D. This is so tiny up here, but on your screen, I wonder if I can zoom in. Zoom in. I don't want to mess things up. Yes. 125%. No. 200%. Yes. More. 300%. Can I move the screen? Oh my god. Yes, I can. Oh my god, look at this. Sorry, new to a smart board. All right, we have x over y plus 1 all over the quantity of 1 minus y over x. Whoa. How can we even factor these right now if we've got that addition and subtraction going on there? Well, let's add and subtract first. Let's deal with that numerator. Currently we have x over y plus 1. These do not have common denominators, so we cannot simplify these and get them into one term. So let's get common denominators. Multiply that 1 by y over y. When we do that, we should get x over y plus well, y over y, all over, and that denominator, here the denominator of the fraction there is x. So let's multiply this one by x over x. So we have x over x minus y over x. All right. We've got common denominators on the numerator and on the denominator. So let's combine these. In the numerator, we'll have x plus y over y. All of that divided by x minus y all over x. Now that we've just got a fraction on top and a fraction on the bottom, it looks a lot simpler, and it's going to be easier to divide this out. So we've got a lot of division symbols happening here. It's important to note that this huge division symbol that we started with in the original problem, that's what we're going to use to keep, change, flip, and go from there. Just watch me do this part. So, dividing fractions, we keep the first fraction, we multiply the reciprocal. Can be seen as changing the division to multiplication and flipping that second fraction. Okay. All right. Let's just multiply these out. Multiplying fractions. We just multiply the numerators together and the denominators together. And I'm just going to keep it in factored form because we like factored form because oftentimes things will cancel. In this case, we get x times the quantity of x plus y over y times the quantity of x minus y. Nothing is canceling. That's okay. We still simplified our answer. But just note that when dealing with these complex fractions, add and subtract within the numerator and the denominator first, and then divide and multiply out from there. All right, let's move on to our final problem on the next page here. So our final prompt with this green star is to rationalize the denominator when needed. So when we have radicals underneath or in the denominator, we want to get rid of those radicals. If you were listening for that square root of x plus square root of h like mini calculus preview the other day, this is where we're doing this officially. So here we have y over the square root of 3 plus the square root of y. And these radicals in the denominator are freaking us out. All right. In order to get rid of these radicals, what we're going to do is multiply by this is a new word, the conjugate. Conjugate. Basically, the conjugate is the conjugate of a plus b is a minus b. It's just switching that addition to subtraction, but keeping the order the same. We use this a lot when thinking about division of squares, as we've seen already today. A squared minus b squared is equal to a plus b times the quantity of a minus b, and that's going to come in handy right now. So if we see these radicals in the denominator, we want to multiply by the conjugate. So we'll have the square root of 3, make this a little bit bigger, square root of 3 minus the square root of y all over the square root of 3 minus the square root of y. We're multiplying fractions, so let's just multiply that numerator together and that denominator together. So we will get, I'm just going to keep that numerator in factored form. In the denominator, we have the square root of 3 plus the square root of y times the square root of 3 minus the square root of y. Watch me FOIL this all out. So we have the square root of 3 times the square root of 3 is just 3. We have square root of y times square root of 3 is the square root of 3y. The square root of y times the square root of 3 times negative the square root of y is minus the square root of 3y, and then the square root of y times negative the square root of y is minus y. This is the FOILed version. These two middle terms are going to cancel, which makes sense. We have a, basically here we have, never mind. 3 minus y. We'll have 3 minus y left over. The rule that I wrote back up here, that a squared minus b squared is equal to a plus b times a minus b, that is where all this is coming from. The square root of 3 plus the square root of y was our a plus b, with a being square root of 3, b being the square root of y, and 3 minus y being a squared minus b squared. So that is it for today. I'm not sure what time it is right now for you guys. If we have finished early and you have extra time, please work on these next problems. It is just this next page. Yep, through problem number through problem number 19. So work through those, and I will see you on Friday. Thank you for listening.